So today we're going to be looking at number of 1 bits. A function that takes the binary representation of a positive integer and returns the number of set bits it has. So if we have 1, 0, 1, 1, we can count that there's 1 bit here, there's 1 bit here, there's 1 bit here, so 1, 1, 1, there's 3 bits. So obviously we can do it using our eyes. How do we do this with a computer? Now there's some concepts that you can use from this problem to apply to other problems. The main concept is, how do we look at each bit? Okay, and the number 2 is, how do we check each bit? Okay, these are the 2 problems that we need to be able to solve using a computer. Obviously with our eyes we can do it pretty easily by just counting, but how would a computer do this using bit operations? That's the main goal here, is to use bit operations to accomplish number 1 and number 2, to replicate what we do in real life with our eyes inside a computer. Okay, so once you break the problem down, it's really not that hard. And first we look at each bit by using the shift. Okay, so shift in Python would look like this. Let's say you wanted to shift this bit string A, you would use this. You would shift it to the 1, for example, or you could shift it to the left by 1. Now, what would our bit string shifted to the right look like? Well, let's assume that A is 1, 0, 1, 1 in binary, so it'd be 11 in base 10. If we were to shift this to the right, it would become 1, 0, 1. So A shifted to the 1 bit would be 1, 0, 1. And if we shifted A to the 2 bits, it would be 1, 0. So do you see that it's moving the bit string to the right? And since it's running out of space, it's getting rid of this last bit, and then it's getting rid of this last bit. So this becomes this. And looking at this, if we repeat this process until we no longer have anything left, our last bit, our bit on the will be the least significant. So not the least significant. We can look at each bit by shifting and just looking at the last bit, because the last bit will in each sequence be every bit of the bit string. Using this, you can see how we can iterate through the bit string and look at each bit, because that bit will be the last bit, the least significant bit. But how do we check what that last bit is? Well, first we need to know what the AND operator does, and we need to AND the bit string with 1. So AND is pretty simple. If you have 2 inputs, for example, I'm going to say C and D, and you want to AND them together, 0, 1 and 1 is going to equal to 1. And everything else, every other C and D is all going to equal to 0. Okay, does that make sense? So what if we AND A with 1? Let's use our same A, 1, 0, 1, 1, and we AND it with 1. 1 and 1, that is, 1. 1 and 0, that is 0. 0 and 0, 0, 1 and 0, 0. Right? What have we done by ANDing A with 1? Well, we've checked what our last bit is. Our last bit is 1, because ANDed with 1, it is 1. So this operation essentially checks what our last bit is. Let's assume, let's go with the other possibility that it was 0. If this 1 was 0, then we would have 0 at the end instead of 1. So either way, we can check using A and 1 what the last bit is. So using this part, we can check, we can get every bit to be the last bit. We can look at each bit by making it the last bit. And using this part, we can check what that last bit is and count how many ones there are, or how many zeros there are, or do something else. So it's important to realize these two parts and how they factor into our final goal, which I'm going to demonstrate using this, which I'm going to code now. Okay, so we have our Hamming weight question here, and let's go ahead and just make our little result variable so we know it's going to be an integer. It's just going to be the number of ones. And how do we do this problem? Well, remember, part one was to look at each bit, right? Specifically the last bit. And how do we move the integer so that we're looking at the bit? Well, we have to shift it. But how do we check the last bit and see that's 1? Remember, that was n and 1, right? This will give us the answer to that question. So n and 1, if n and 1 is equal to 1, that means we have a 1 as our last bit. But we don't just want to look at the last bit, we want to look at every bit. So how do we look at every bit? Well, we just keep shifting our bit string. So n is greater than 0, okay? Because obviously if n is 0, there's no more work to do. But if it is still greater than 0, what we can do is shift it to the left, or excuse me, to the right. And we don't want to do that before, we want to do that after we check. So we check the last bit. Let's walk through this input string. We check the last bit, is it 1? Okay. If it is, then we add 1, and then our result will now be 1. And then we shift to the right. So now our string is 101. Now we check our last bit, is it 1? If it is, we add 1. Now our result is 2. So we shift it to the right once again. And now we look at our last bit. Our string is 10. N is 10. We look at 0. Is 0, 1? No. So we're not going to add anything. So we're still at 2. That now we shift to the again. Now our n is just 1. And if 1 and 1 obviously is equal to 1, so we add to a result and we have 3. So it looks like our answer will work as long as we just return our answer. And that should do it. Let's see, we're passing these cases. And I'm going to go ahead and submit. So yeah, that solves the problem. And I hope this was useful.